Imagine a deeply misleading mathematical term, random variable. It sounds intuitive, yet it's neither truly random in definition nor a variable in the traditional algebraic sense. This isn't just semantics. Grasping this distinction is crucial for a solid foundation in probability theory, preventing common misconceptions. When you hear random variable, you envision an unpredictable value changing haphazardly. You might picture rolling a die, its outcome being the random variable. While this relates to its application, the mathematical object is more precise and, surprisingly, less random than its name suggests. In algebra, a variable x represents an unknown quantity, or a numerical placeholder that changes. We solve for x, or analyze its behavior. This is a direct numerical representation. A random variable operates on a different conceptual level, introducing abstraction. First misconception: a random variable is not an algebraic variable. It is a function that maps outcomes from a probabilistic experiment to specific real numbers. This transformation is deterministic, not random, inherent to the variable itself. To understand this definition, recall basic probability concepts. Every experiment has a set of all possible outcomes, the sample space omega. An event is any subset. Rolling a single die has a sample space of 1, 2, 3, 4, 5, 6. Formally, a random variable x is a measurable function x, omega right arrow math bar. It maps each outcome omega and omega from the sample space to a unique real number. Randomness stems not from the fixed function x, but from the outcome omega realized by the experiment. Consider flipping two fair coins. The sample space omega equals HH, HT, TH, TT. Define x as the number of heads. Then x, HH, equals 2, x, HT, equals 1, x, TH, equals 1, x, TT, equals 0. X is a consistent, fixed mapping, deterministically assigning a number. Second paradox: a random variable is not random. The function x is a perfectly defined, deterministic rule. Given any specific outcome, it will consistently produce the same real number. No inherent randomness exists within the mapping function. It's like saying equals x squared is random. It is not. If the random variable isn't random, where does it originate? Solely in the underlying random experiment generating the initial outcome from the sample space. It's the unpredictable nature of the coin flip, or die roll, that makes the random variable unpredictable the experiment. Once our random variable is defined, we quantify its outcomes through its probability distribution. This distribution describes probabilities associated with each numerical value the random variable can take. For our two-coin flip, p, x equals 2, equals 1 over 4, p, x equals 1, equals 1 over 2, p, x equals 0, equals 1 over 4. Random variables are categorized into two types, discrete and continuous. Discrete ones, like counting heads, take finite or countably infinite distinct values. Continuous variables assume any numerical value within a specified interval, often from measurements such as height or temperature. Why did random variable persist? Historically, intuitive usage precedes formalization. It likely refers to the assigned contingent upon the unpredictable outcome of a random process. Remembering its functional nature is key for precise understanding. Understanding a random variable as fundamentally a function, not a fluctuating number, is crucial. It forms the cornerstone for a rigorous mathematical framework in probability and statistics. This distinction is vital for modeling uncertainty across diverse fields, from finance to physics. In summary, a random variable is a deterministic function transforming unpredictable outcomes of a random experiment into numerical values. Randomness originates solely from the experiment, not the function. Grasp this core concept, and your probability journey will be clearer.